This presentation is going to review pulleys. Pulleys are a grooved wheel, and a rope or a chain can run inside that wheel, inside the groove, and it helps to move objects. Now, as we've learned with other kinds of machines, pulleys themselves cannot reduce the amount of work done overall. So a pulley can also change direction or can change the amount of force required and or increasing the input force on an object. Now pulleys are a kind of lever. So if we were to look at an example, so if we look at the wheel and there's rope going through that wheel, we pull down, you have an output force and an input force. Just like if you're looking at a lever, and you had a fulcrum, you'd have an input force and an output force. So the fulcrum of a pulley would be the center, and you'd have the input and output forces, very similar. Let's look at an example. Here is a 1 kilogram mass. It is on a force sensor, and a 1 kilogram mass would have 9.8 newtons worth of weight. Let's see what happens when we put this weight on a pulley. In a single fixed pulley, the input force is essentially in the opposite direction of the output force. So if you're raising a weight, a single fixed pulley will cause the weight to go up, and your input force, the string, would come out the other end. Now, the mechanical advantage of this machine is 1 to 1, or 1 mechanical advantage. So if our weight is 9.8 newtons, our required force is going to be about 9.8 newtons. So we can plug that in. 9.8 newtons over 9.8 newtons is 1. So the mechanical advantage is 1. Now, the quick way of finding out what the mechanical advantage is of a pulley is to count how many strings are holding it. One string supporting our weight here is just one mechanical advantage. This is showing a movable pulley. As we've seen in the movable pulley, the effort needed in order to move an object is quite different. So as we saw in the example, it's going to be easier to lift a 9.8 Newton mass with a movable pulley. As we can see here, there's an attachment that's going to be stationary, and the pulley is obviously moving from its name. And each one of our strings here is going to be holding onto our weight, and essentially, each string is going to be holding about 4.9 newtons worth of the weight of our mass, right? So each string. That means, if we're looking at the mechanical advantage of a movable pulley, the 9.8 newtons worth of force is being compared to the 4.9. So if it's a ratio, it's going to be 2. So the mechanical advantage is 2 of a movable pulley like this. This special setup is called a block and tackle. As we just seen in a block and tackle, we can also reduce the amount of effort required. As you can see, there are two strings that are holding up our pulley, and each one of those strings is holding onto our mass of 9.8 newtons worth of weight. And since it's being distributed again, we can say it's 9.8 for our mechanical advantage over 4.9, and we get a mechanical advantage 2 here because there's two strings. This is another block and tackle, but it contains 6 different pulleys. if we look at the number of strings supporting our weight, so the weight would be beyond the screen here. So it's 9.8 newtons, right? We have strings 1, 2, 3, 4, 5, 6 strings holding up this block and tackle. So if we're to think of the mechanical advantage here, the mechanical advantage is our 9.8 newtons over the effort force that we put it in was 1.63 newtons. So our overall mechanical advantage here is 6. This is correlated to our number of strings 1, 2, 3, 4, 5, and 6. As with any simple machine, if we're reducing our amount of effort force, you're going to have an increase in the overall distance that you're going to be traveling. So, when you're using a block and tackle, for example, and this particular one that's on the screen here has 1, 2, 3, 4 strings, right? That gives us our mechanical advantage of 4. So it'll be 1 Newton worth of effort to lift it, as we can see on the picture there. But the truth is, the amount of string you'd have to have come out would have to be the equal that distance. So it would be 4 times the amount of string needed to lift it up if we were just going to lift it straight up into the in a vertical position. So as we always say, you cannot destroy work. So the work in has to work equal the work out as a basic definition.